still some people joining, but I'm going to start the webinar. I want to thank everyone for joining today. I just want to make sure, Debbie, am I audible? Everyone can hear me?
You are. Thanks, Kobus.
So today we're going to have a webinar regarding tower masts, so tower and mast structures. This is sort of one of the webinars we've been working on since last year, going into a course, but we'll talk about that a bit later on. I think just to start off with you guys, just some background on the structure division. So SAICI structure division is the biggest division in SAICI. Our membership is about 6,332, but we only have 44% in good standing. So what good standing means for students, it's meaning you just have to submit your proof of registration to SAICI, then you're in good standing, and members themselves need to pay. So our members at least are on 84, but I request, I think most of you guys probably in this meeting have paid, but if not, please, can you just pay your SAICI? It does assist us getting funding to do a lot of the stuff that we are doing. And then students should get a lot of benefits from being a student member at SAICI. Yeah, so thank you guys for the guys who are up to date with their payment and stuff. I think then I'll just go to the tower mast structures. So just some ground rules on today's webinar. So if you have any questions during this presentation, please just type it into the chat, and then at the end we will answer it through whoever needs to respond. And then those we don't get to, if we run out of time, we will then put out an email to answer all those questions for you guys. I just sort of, before I start, I'd just like to tell you guys some. So this webinar came from Syntec, and it's an idea that we got from Syntec regarding there's not a lot of engineers out in South Africa with this type of speciality in tower and mast structure, and we as SAICI saw there's a need for us to let our members know about the specialty field, if you can call it like that. And then we did this webinar as an introduction to a course that we are planning. The course date so far is the 15th and 16th of July, and that will be held in Midrand in person. I think we will, as soon as we send out the invite, we'll see what the need is in everyone that wants to attend the course, and then we can try and see if we can push it into Cape Town and Durban. But so far we only have Midrand that we're planning. So please keep your eyes on any invitation that's coming you guys' way. I think, and then this is sort of just start off with the webinar we're holding. But I think before Dr. Breda and Dr. Mohammed starts, I'm gonna give chance for Akile and Gary. They are representing Syntec to give a short presentation on what Syntec is and does. I think they'll give themselves background, introduce themselves. So I'll give over to you, Akile. If you want to share start your presentation.
Sure. Thank you so much, Kobus. Can you confirm if you can see my presentation?
Yes, we can.
Yes, we can. Thank you.
Colleagues, I just switched on the video for a second so that you can see that you're not talking to a robot, but for the bandwidth, I'm just going to switch it off, and when I'm taking questions, I'll switch it back on again. Colleagues, thank you so much, and I hope
I'm sorry,
everyone
Nakile.
Yes.
Your presentation is visible now. Thanks.
Oh, okay, sure. Okay. I hope everyone is well, especially in this cold weather. We are in Joburg. So my name is Nkile Mutsewa, colleagues, engineering manager for Syntec. and it's quite a pleasure to be invited to this webinar and to engage with you on what we do, as well as how we can collaborate and benefit from your support. So I'm going to be giving this presentation supported by Gary Pio. He's our civil specialist. He'll introduce himself when the opportunity comes. And also have Bongani Masondo on the call. He won't be presenting, but he's also a civil specialist under Centec. So our presentation will be very brief. We'll introduce Centec, as I've mentioned. We'll provide an overview of our infrastructure, highlight some of the key challenges we have, and also touch on the opportunities for collaboration and mutual support. So who's Centec? So Centec is a state-owned company that operates under the Ministry of Department of Communication Digital Technologies. And our service offering, the span across broadband, media, satellite, and managed infrastructure businesses. But today's presentation will focus mainly on the managed infrastructure business. So we do have a footprint nationwide. So you'll see our mast everywhere you go in the country, primarily on top of the mountains. And it was established in 1992 from SABC. Before 1992, SABC was the main signal distributor, and beyond 1992, Centec took over. So as you can imagine, our biggest client will be SABC. And so due to the uniqueness of our mast and the fact that we operate in different environmental conditions, we always find it quite difficult to get the right skills when it comes to the structural audit. So Gary will come and talk about this, but I just want to introduce the topic. So we have a different type of mast across the country, and dying on top of the mountains, dying areas where we have snows, dying areas where we have different, environmental conditions, and they are quite tall as compared to other masts from other telecommunication companies. And this mast, they are tall structures, and the time to time we need to go out there and get an engineer to say, are we still safe? Can we still put more weight on the mast? What's the wind loading like? And we went a couple of times, to the market in terms of trying to attract those engineers, and we struggled. We put together like a panel of contractors to say, do we have engineers in the country who can do that for us? The first time around we went, we only got two companies. Second time around, we only got one company. But I'll tell you more about the opportunities, and we now planning to go out again to the market. So the whole point of this presentation is to maybe spark some interest in you as a civil professional. Maybe you can look at our tender, but then I will allow Gary to come in at this point and tell you more about the mast and interesting things on what problems are we facing, and where can we work together to close those gaps. Gary, are you on the line?
I am indeed.
Okay. I'll keep on presenting. You'll just direct me to move the slide.
I can just, I want to share actually the full photos, if I can. Yeah.
Okay.
Okay, can you see that photo?
Yes.
Okay. So afternoon, everybody. And Sasi, thank you for the opportunity. I really appreciate it. So as Nikili has said, we have a large network of both freestanding lattice towers and stayed masts. stay lattice masts. So, you know, everything up to about 279 meters, that's our tallest stage structure. This particular photo that I'm showing you now, this is actually just a 157 meter high mast. This is what Centec would call a standard Liber 570 foot mast. So just a little bit about this particular photo. What we are seeing at the moment, if I can just zoom in there, this building on the left is our TV building, and this is a typical house site, Centec's typical house site. We have a TV building. This is a newer building. On the right of the mast is the old FM building. That would have been the first building that was put down in the 1960s. Then TV came along in the 1970s. This multi-story reinforced concrete structure came up. So this mast would have been put down, but typically just with the FM antennas at that particular point there. Now, the 570 foot mast would have just had 3 levels of guy rope. So what you are seeing here, there's an additional guy rope. So when TV came, well, actually, this was additional to TV. The TV spine is over here, and we added additional guy rope, and that came along for DTT. So a nice oval picture of what a Centec mast looks like on a house site. A lot of the typical things, you see a tapered bottom structure going to a pin joint at the bottom. Our masts, typically the older masts, have a K-type bracing going up to a particular point in the mast, which is generally at the top or second to top guy rope level. And from there we have a Z bracing type, where typically where the FM antennas sit, we have a Z bracing configuration. Mast then tapers at this point over here for the TV spines. So that is very typical of what we have with the older structures. And this typical structure here is all imperial, feet and inches on the drawings. That's what was put together in the 60s. And here we have a nice little picture showing a typical FM antenna panel array, generally 4-face, not always. This would have been the main platform. When TV came, this would have been the initial TV VHF TV panel array, often 4-face, not always 4-face. So on this one as well, this is an additional guy rope that was added to the structure to accommodate a new spine for the UHF antenna, which came along for ETV. So quite a generic picture of what is happening at the top of our masts. And these are transmit antennas for FM and TV. Further down the mast, we have the Centec receive antennas, as well as on a lot of masts, a lot of site sharers with panels, dishes, etc., etc. So the masts are quite popular, especially in certain areas, very popular, and the uptake in antennas on our mast have been significant, and Centec has also seen this as an opportunity to lease out additional space. So this is what it is meaning for Centec, is that we are having to relook at our masts to ensure that we are compliant with current regulations, as well as capacities, etc., etc. So there is going to be a phase we're going into now where there's going to be a lot of work happening on our masts. So upgrades, audits, even some of the maintenance tasks. So quite a bit of stuff going to be happening on our structures. Here's a nice picture of the base of the mast, nice pin joint at the bottom over here. Nice taper. Face width of these around 2.3, 2.4. Okay, it's an anchor block. You can see this anchor block here has been added to, and we added a new guy rope. So we augmented the anchor block. This particular one was either a 670 or 770 mast, 4 original guy ropes, and 1 additional guy rope. In terms of adding or upgrading a mast, this is what we do have on one or two of our masts as well, where we added an additional antenna spine. And this we call a diamond stay. It's not very common, but we do have this on 2 or 3 of our structures. Our guy ropes are greased, so we do have rope dressing on them. So also vibration dampers. This is a typical Stockbridge type vibration damper, top and bottom on the guy ropes. Some of our masts have been strengthened as well. Mast leg with a double angle welded, fully welded to a mast leg. That's a picture of some additional strengthening done to a mast spine. So this is that VHF antenna that you saw previously. And here we have a bolted angle situation on the actual spine, just to beef up that spine area. Another picture a little bit further down where the taper is, a little bit of strengthening done on the face of the mast with some horizontal bracing. Also a bolted scenario. So that's just a brief overview of what and typically what Centex high sites are. So we have had over the years various spurts of activity on our structures. You know, we had the initial thing in the 60s with the network being put out with FM. Then we added the TV that came a little bit later in the 70s. In the early 2000s, we increased our footprint by adding some new structures. And then again for DTT, we added a whole lot of new masts as well. Some taller ones, some smaller ones. So there has been spurts of activity on our network and also on our masts. So I see that our next phase is coming in now. So there is going to be quite a bit of activity happening. And as far as, you know, location, we are countrywide. We have everything. We have snow, we have ice, we have salt, chemical, corrosion activity. We have blasting activities adjacent to some of our sites, coastal, inland, in the Karoo. So scour perhaps by wind sand type of wind scour. So a lot of activities exposure on our sites. Extreme temperatures, humidity, mist. So all of that stuff is happening all over the country. So I think that's all for now. So Nikele, I will go take back to you, please. Nikele, we're not hearing you.
Oh, sorry, colleagues. I was talking to myself here. Yeah, thank you so much, Gary. So I was just mentioning that Gary did touch on the type of mast, the type of strengthening that we have done on the mast, and you know, different types, different environments, and you can imagine the type of problems you're gonna have on the mast. You can imagine if you have a mast next to a mine, what's gonna happen to that mast, and what type of problem you're gonna have. So when we do go out to the market and ask for structural audit of such type of mast, so we really need, you know, people who are, or what we are seeing rather, we're seeing that for the same type of mast, we'll get different results. You know, one engineer will show us, okay, this is your mast is overloaded. This is the problems you have on the mast. And we'll have a different engineer who will come up with something different. And this is the base of why we are here, and maybe why SAIS is also helping us in putting together training so that we can find like a common point amongst the engineers, so that whatever we're getting from the engineers is almost the same because we're using the same type of knowledge. So that's the constraints that we are picking up. I did mention earlier on that we on this type of mask, like there is we're going through a certain phase now, where we upgrading, strengthening some of the masks, and also putting new masks on our side as well. And you can imagine if an application comes to your desk and someone wants to put an antenna and I have to decline it. But when people go to site, physically they can see a space there. So you start not sure whether what you're seeing on the audit report is correct or not. So I'm trying to show you the type of problems that we have, and the reason why we needed this training, and the reason why we want to spark this interest on you. And maybe you can take this as a postgrad, or maybe you can think about it also for your business as well. So yeah, we do have we've seen that we have a limited experience when it comes to this. We've seen some inconsistency when it comes to audit, and now it's being reported to us as well. So when it comes to now opportunities, one is we're looking for, and I can say this here, I think be lookout, check our tender bulletin. We should be issuing out a tender in a week or two on the structural audit, where we'll be asking for companies who can do structural audit for us. Please, if you know someone who can do it, or you can do it, please, we'd like to see your proposal in that. But yeah, we are looking for competent professionals on doing the structural audit. What we are seeing is, we're starting up with the second phase of our master, where we're doing a whole lot of structural audit. And we're also seeing engineers using different type of softwares, which is not a problem, but then they're supposed to give you the same result. But they are not. So those are some of the pain points that we have, and we're hoping you as an industry can help us to say, can we have some way where we do these things and we do it the same way, whether you are using software A, software B, or it shouldn't be, the error difference shouldn't be more than 10%, even 5%, I think we are pushing it there. So we're looking for competent professionals who can help us with the structural audit, who can help us with the design. We're putting to get a new mast on our sites, and also be creative in terms of strengthening the mast. We co-locating on our mast. We have application coming from different people who want to put antennas on the mast. The mast has limited capacity, but we now asking question on, can we increase the capacity, and if we can, by how much? Can we, and if you can increase it, can you increase it by 10%, 50%? What's the maximum we can go on this type of mast? How can you maximize it, and how much can you maximize it? And even though you can maximize it, can you be creative in how you're strengthening that as well? So those are some of the problems that we have, and we are asking for competent, professional to come and assist us in strengthening all this mass, because for us it means a business. Because once we strengthen it, we have enough flat plate area, we can accept more people on our mass. Safely so, because one thing we don't compromise on is safety. We don't approve anything that we feel is not safe. We need. I was talking to Kovas about this, but we at some point, once this is in full motion, we'll have to start talking about standardization, especially a South African-based standardization. And that's where you're gonna need your expertise as well to say, we have this standard, call it TIA, what are other standards, but are they talking to us as South Africa? Do we have different conditions that maybe are not covered by this standard? Maybe not, but then we need someone to, formally check. And if not, we need to have adopt the standard for South African conditions. So those are some of the things that we want to encourage you to collaborate on. And research as well, we are open, colleagues. We have different type of problems. We have snowing on the mast. We have masts that are closer to the mines. What's the cheaper way, or what's the easier, efficient way of monitoring this mast that is still safe? You know, do you want to put vibration sensors? What? So we are open if you were to approach us to say, I'm interested in this. What are your pain points? And then you can share with you the pain points, and you can come back and say, I want to go pursue a PhD or a master's. Can I look at this one? For sure, we'll do the internal approvals, but we'll surely support you, because that will mean that you're going to be helping us, and then not just us, we're going to be helping the country as well in building the skills in the country. So that's the opportunity that we are seeing in this, and we more than willing to work with you in helping us closing all these gaps. I think that's about it, colleagues. I don't want to go very long in this. I think we still have about 2 more presentations, but then I'm hoping that you understand what we do as Centec and the type of structures we have and some of the pain points. And you're also seeing opportunities where you can, work with us to close all the gaps that we mentioned in this meeting. Uvers, back to you.
No, thank you, Gide. Appreciate that. Yeah, I think then we'll just jump right into it. So I'm just going to let Dr. Breda and Dr. Mohammed introduce themselves, and then they can take the presentation. Dr. Breda.
Good day, Mr. Chairman and SAICI members as well as guests. My name is Breda Straslam. I lectured at the University of Stellenbosch in structural engineering till about 6 years ago. Also did a little bit of work after I retired. In our one course, we also had a section on cable stayed structures and masts. So I've sort of picked up from that and then prepared a presentation with a little bit more meat to it for presenting this afternoon, Mr. Chairman. Can I carry on with my presentation?
Yeah, you can carry on. Yeah, 100%. Yeah.
Okay, fine. So I'm going to introduce the Mast and Tower structures part of this presentation this evening, or this afternoon. What's going on here? So we're going to look at structural design, construction, and maintenance of tower and high mast structures. I've got about 30 minutes allocated, so let's see how it goes. So let's just look at my topics I'm going to deal with. Number one, we're just going to look at the structural format and design criteria for towers and masts, some design codes which we have worldwide, some loading considerations we can think of. They're probably not complete, but giving one a good idea what it's about. And then we can just look at the topics in solid mechanics leading into the applicable structural analysis for towers and masts. And then I'll do a little bit on dynamic analysis, but Mohammed will follow on with much more on dynamic analysis of towers and masts. I'll look at a few software products which are around, and then a little bit on fabrication and construction and structural maintenance and refurbishment. And then I've also got just 2 examples of structural failure. So let's look at some masts and towers and structures in South Africa. We've already seen about Stentec. The other ones I could identify, I might have a few of them which I might not have identified. Telkom has about 4,000 plus masts, which are managed by a company called SwiftNet, which is also a state-owned company. And then Vodacom in 2022 formed a company called Mast Services, which also manage all their masts. And then MTN has a company called AHS Towers, which manages about 5,700 masts for MTN. And then I think another one I could think of was South African Air Force and Navy. They also have mast and tower structures, but I think they might be linked to the Department of Public Works in that environment. So there we are. This is the South African Air Force at Waterkloof Air Force Base. This is the VHF, if I'm not mistaken, masts for the communication with the aeroplanes. Interestingly enough, I talked to a colleague of mine, or actually a person which I know in Pretoria a while ago. His son flies for Emirates, and he likes to look at the flight radar when his son's flying, but we said when they actually fly over the pole from Dubai to, let's say, for example, San Francisco, then at a certain latitude, they don't use the satellite systems anymore. They actually switch to the VHF. So this is still a very active communication and navigation system which gets used by aircraft. We all know about Telkom's Lucas Rand Tower. That's one there. And then as I drove around the last few weeks when I knew I had to do the presentation, I just took a few photographs of masts. So these are 3 masts in Kleinmond in the Western Cape, cell phone, and then also the security company's radio mast. And in Rawsonville, one finds this quite impressive mast there, which also seems to be related to cell phones. And then there's a company called Telecommunications Masts and Accessories in South Africa, which has a website with quite a number of examples of their products on it. And also have experience in working with a person. I don't think they actually in this, the company is not in this format anymore, but they were working on light duty masts, for example, for instrumentation. They did quite a lot of work for the wind power and wind turbine industry to actually put up masts to sample wind speeds and things with instrumentation at certain sites where they were working on developing their wind power. Rawsonville has got quite a high cell phone mast, and there you can see the base of this structure with the supporting lattice work there to keep this mast upright. And this is the one I photographed in Uniondale. As you can see, this is quite a challenge because of the security situation around these masts and people trying to damage them or vandalize them. In this case, on this side, you can see they've got like this concrete bunker unit. They probably lower it down on the generator, the power generator, which is linked to this mast. And if they want to work on the generator, they actually lift up this whole concrete bunker. And you can see here the kind of wiring and razor wires they need to actually keep people away from their equipment. I know that in the Bottlery Hills near Stellenbosch, in South Africa, near Stellenbosch, they actually have security guards which come in, I think, at sundown and then live next to the mast on the hill there until sunrise again. The typical structures which one finds in the mast and tower environment: monopoles, lattice towers, either freestanding or guide or cable stayed. Some people use the word guide, some people use the word cable stayed. Concrete columns and towers and masts, timber towers, and there are, of course, all sorts of other forms of communication structures. So if we look at some examples, I just took this from MTS Tower's website, some samples of kind of construction formats one finds. There's a very wide variety depending on what kind of load one needs to put onto the structure and what kind of environment it needs to operate in. One can come up with a wide variety of structural formats, both in monopole format as well as in a lattice structure format. On this MTS website, they also have some examples of structures. You can see in this case they have a pipe section on their main members. Sometimes you also, on the lighter structures, you have angled members. Here's a guide mast and then a radar tower. And of course, this is the camouflage tower one finds all over South Africa to disguise the cell phone tower environment. It's a cell phone tower and disguise it so it sort of blends in with the environment. And I must still say, although we're not dealing with today, one must just take note of the power industry transmission line environment, which has a similar kind of approach to keeping their cables in the air. So if we look at the design criteria for towers and masts, this is sort of the overall one. Typically, there's a structural and electronic requirement. And on the electronic side, you have low frequency, medium frequency, VHF and UHF, digital audio broadcasting, as we heard, and then mobile phone antennas. And then you also have microwave structures or microwave transmitters, which need to be supported by these structures. And of course, there's corrosion and fatigue, which one needs to look at, and then also seismic loading in some cases. On the structural side, we need to be able to work with truss models, beam models, and cables. And we also need to look into structural displacement requirements for both the static and the dynamic loading. On the wind loading side, We have the long wind response in the direction of the wind, and also, as we'll see in a while, there's a whole issue about crosswind response, which like vortex shedding and galloping, which one that has to take into account both for your cables guys as well as for your rest of your structure. Then, if you look at the stability considerations, you have the global structure must be stable, the element or the component must be stable, and our section must be stable. So we need to do quite a serious investigation into our structure to make sure that we're getting stability. And then, of course, we need to do structural component design and look at fatigue and buckling considerations. And then there's also specialists typically involved in looking into our foundation specifications. And then the whole story, as we've seen, our anchor blocks where we need to anchor some of our cables. These things need to be designed, and our base needs to be designed for uplift, overturning, anchorage, and then foundation bearing considerations. Let's just look at the design codes, which I could find. Well, this is a sort of worldwide: South African, UK, United States, and Australia, and Canada. So the first one I've got here, where you find a specific design code for steel structures on towers, masts, and chimneys, is the Euro Code 1993. And that links to this, that's on the steel side, that links to the Euro Code 3 Design of Steel Structures document. So in this document, you'll find guidelines for design of your steel structures for towers and masts. Then in the United States, there's probably a universal building code as well, probably linked to something linked to the universal code, but the one which is quite well known is ASCE 7, design loads for buildings and other structures. And then on the tower side in the US, the American National Standards Institute is linked to the Telecommunication Industry Association, which has a document TIA 222, which is structural standard for antenna supporting structures. And interestingly enough, you can also, we've used this quite extensively on the seismic side. ASC 722 has a so-called hazard tool or a website where you can actually, I'll show you in a minute, where you can actually get estimates and calculations of your loads on your structure. So there's your United States codes, your ASCE minimum design loads code, and then your TIA standard for your antenna supporting structures. This is the view of the website of ASCE 722. It's a very extensive website, and it purports to be usable right across the globe. I don't know, one will probably have to check it out and make sure that you're happy with the numbers coming out of here. But this tool can provide wind loads, seismic loads, ice loads, snow loads, rain loads, floods, tsunami loads, as well as tornado loads for any site, according to this website, for any site on the globe. In Australia and New Zealand, one has this 3995 AS code, which then is specifically for lattice towers and masts. And then, of course, you also have the link to these normal structural design codes, which you have, which are applicable in Australia and New Zealand. Canada, there are two Canadian codes, which I'm just going to mention here. The one is the S37, which specifically also deals with antennas and towers and antenna supporting structures. And then the S16, which is a steel structure design, which of course links to this previous document. South African steel design, SANS document, was developed with reference to this Canadian steel design structures code, as far as I know. So that's not, I think it's still not a link to the Euro code, as far as I know. Although we're now switching to the Euro code on the concrete side. So that's interesting anomaly we have at the moment, but it's probably something going to happen there in some time in the future. There's our Canadian code documents, so just the front pages for towers, and then of course the steel construction document. South Africa, we all know about SANS 10160, parts 1 to 8, and then we have our structural use of steel 10162 for the hot rolled steelwork, and 10162 part 2 for the cold formed steel structure. So that's, but we don't have any specific document in South Africa dealing with towers and masts. I think what's his name again? He was mentioning that we probably need to look into some standards for the South African environment. So let's just look at the structural loading. I'm just going to mention a few, not everything. So we have the own weight, static wind loading and wind resistance, dynamic loading, crosswind, as well as vortex shedding. Then we have ice and snow loading, seismic loading, and then maintenance crew and maintenance procedure loads. When in certain cases, components of these towers need to be replaced. For example, sometimes your guide cables need replacement. In that case, you need to be in a position where you can support the structure while you're replacing specific components of the structure. So as far as the wind is concerned, we have our standard long wind loads, which we can get from our codes. But then we have something like, which we have to consider, that the wind resistance of a tower due to ice on the structure can change dramatically. This is just an example which I took from the book by Smith on communication structures. You can see that your structure can actually ice quite well, the ice load on the structure is quite important, but it's also changing your profile, your wind profile for your long wind response of your structure. Another one which one needs to take note of is the so-called vortex shedding concept. So if we have wind blowing from this side, then on this structural component, which is just represented here by this semicircle, you get so-called eddies, or well, you can call them, you can call them, probably call them vortices, not eddies, vortices, which form behind this structure, and then you get vertical motion of the structure due to the wind movement from left to right on this screen. There's the basic formula how you calculate your critical wind speed, and this critical wind speed, interesting enough, is not very high. It can be just a few meters per second depending on the structure, where this phenomenon can start playing a role. There's also a number here, a dimensionless number, which appears in the formula, which for our example is typically in the order of 0.2, the so-called Strohal number. So there's our parameters, but I don't think we need to look into that for in more detail. But of course, when you start looking at inclined cables, you need special calculations to make sure that you can account for this vortex shedding situation. And you also need to calculate the frequency of natural frequency of vibration of your cable. There's a very basic, natural frequency calculation for a cable which is under tension T with an M. The M is the mass per unit length, and the L is the length of the cable. So you can calculate your cable frequencies for your mode shapes of the cable. So let's just look at the crosswind response a little bit more on vortex shedding. So we can decide whether we're in the laminar or turbulent flow environment. Typically in the wind case, we're in the turbulent flow environment, and then we have to estimate the drag coefficient that will determine the force being exerted on our structural component. And this Strohal number is a structural behavior link to compute the vortex shedding using vibration frequencies and determine the displacement under the vortex loading. So there's a graph showing you your drag coefficient versus Reynolds number. Typically in the environment we work is 10 to the 5, or that's before and after 10 to the 5. So the Reynolds number is more or less shown. The Reynolds number is about 10 to the 5. So our drag coefficient is in a region of 0.5, let's say 0.3, depending on what your situation is. And then the Strohal number, if you plot that against the Reynolds number, then you find that in the environment we work in 10 to the 4, 10 to the 5 over here, more or less, this value of the Strohal number is reasonably constant, and we can actually assume that 0.2 is a good estimate. Then there's also a thing called aerodynamic galloping of cables or flexible structures, and there you also need to compute the critical wind speed when this phenomenon might appear. It also happens that when your cables start icing, that your cross-section of your cable changes shape, and that can have the effect that this galloping occurs much more, well, at a lower critical wind speed than you would expect, or might be at a different wind speed. So in this case, you have the so-called Den Hartog coefficient, which you calculate to this term at the bottom here, which is a combination of your drag and your what is CL again? I'll just have to check that out. This term over here, which you need to calculate to estimate this critical aerodynamic galloping wind speed. I just want to show you an example of what happens when, sorry, what's happened to my, Just hang on 1 minute. I just want to find my presentation here. Oh, sorry, I want to stop sharing. Oh, sorry. Seems to my I'm in my That's interesting. I might have pressed the wrong. I'm in my PDF version. So sorry about that. But this in this case, I've got a video which. Oh, there we are. Here's the video. Sorry. So there you could see the effect of this vortex shedding or gallop. It's more like vortex shedding or the wind blowing across this parking boom. This is another interesting thing. What do you do about vortex shedding? You actually provide these so-called helical strikes or fins on your structure, as you see over here. You see this on chimneys specifically. This is the NASA Artemis launch vehicle, not launch vehicle, launch building or structure, which was used for this latest moon. Was it the moon's the project to go to the moon? And here they have these. They've got 3 of these high towers. They're about 100 meters high, and they also cable stayed. And they have these fiberglass units at the top, and then they have cables which are stretched around this or spanned around this launch structure. And the main reason why they are there is to avoid or actually react to lightning strikes. If there's any, they form, these 3 towers form a so-called Faraday cage around this launch structure, so that in case there's a lightning strike, the lightning is not relayed through this rocket or any of these very critical electronic components which go with the. Of course, there's lots of fuel involved here as well that go with this launch. So it's interesting to see that in this case here, you see this. There's a little bit of a larger version here. You see these helical strikes which are put onto the vertical fiberglass columns to ensure that we don't get undue vibration due to vortex shedding in this case. As far as structural design is concerned, one can think of, you typically can use your normal SANS 10162 and your standard Institute of Steel Construction documentation. You can think about using high-strength steels, but we'll probably have to look at the availability and the pricing of that. And then there's some special triangular sections which one can use when you have triangular towers. And you must think about a thing called design assisted by testing, which is mentioned in your code, which is typically also used in the transmission tower, electrical transmission tower environment. When you start producing a relatively slender structure, then you can go into and actually test a full-scale model to make sure that it's up to spec. And then once you've done that, of course, you're going to manufacture quite a large number of these things if you think about power line pylons. And then you can probably save quite a lot of money by physically testing this product and making sure that it's up to spec. Okay. So there we are. I think we've all seen these books. South African Institute of Steel Construction. Reference material will definitely support you when you start designing these kind of towers. And then there's also a book. I think there's a newer version available, but there's a CSR SAIC Designer Structural Steelwork Handbook, which is quite useful if you need to brush up on this kind of material. This I just wanted to show you the special steel sections. You can get a 30-degree so-called shift-polarized angle section, which you can use on a triangular tower, and you can also use this modified angle iron. They add on these extra sections over here, and you have another section which will give you a 30-degree angle. And of course, in this case, you can also have a round. On lightweight towers, you probably have a round vertical section for your vertical structural components. Something on dynamic analysis. Typically, these structures are subjected to dynamic forces in the form of winds or seismic loads. So you need to actually calculate your mode shapes. So this is just conceptually a mode shape of a tower. And here's conceptually the mode shapes you find, dynamic mode shapes you find for a guide or a cable stayed mast. I had to do some work quite a number of years ago on a 55-meter lattice tower in the DRC, which had problems where certain members were buckling under high winds. So we did a full analysis of this tower, and this is just some few of the dynamic mode shapes which one found in this case. This is now mode 1, mode 2, mode 4 is like a vertical mode. Mode 9 was an interesting mode. It was just at the bottom of the tower there was like members which were like twisting into each other. Then there's also this interesting mode 10, which looks like basically the tower is busy inflating. And then in this case we also have mode 12, which is an asymmetric mode with buckling taking place, or not buckling, displacement taking place at the bottom in this mode. And this is an important thing one must take note of. One also has torsion modes in these kind of structures. I've had experience of one tower which failed in the DRC, but there was not a transmission tower or a telecommunication tower. It was actually a tower supporting a bridge, a cable bridge. And this structure failed due to this torsion mode. And this is just an example. In this 55-meter lattice tower also has a torsion mode, as you can see over here. There's the participation factors for all these mode shapes. And you can see, interestingly enough, that 73% of the mass is accounted for in your dynamic analysis if you use 20 modes. Mohammed will also probably talk much more about dynamic analysis. So if you have 20 modes in your dynamic analysis for your modal response, you're getting 73% of your mass, which is actually taken account of. And you can see some modes like mode 2, mode 4, mode 9, mode 17, and mode 19. I think 17 was this torsion mode. They contribute quite seriously to your total mass participation for your dynamic analysis. Then we also looked at the buckling because of the buckling problem. Here's just a few list of the loading cases we looked at, and there's the loading combinations according to SANS. And then we did a buckling analysis. Load combination number 8, we had a buckling factor of about 28. That was just self-weight. But then load combination 9, when we added the wind in the X direction, we found that we were sort of critically close to a buckling situation. And also if the wind was a little bit stronger than we expected, then at load case 14 was also indicated that there might be a buckling problem. So if you look at the mode the buckling shapes, in this case for load combination 8, we see this. This is now just for own weight. And load combination 9, there was just this one element over here which is buckling, but then load combination 14, there were quite a number of elements or components of the structure buckling over here. And this was then actually manifested itself in the field, where they had to go in and replace some of these components and strengthen them because of this buckling problem for this tower, which under high winds. So dynamic analysis, we'll hear a little bit more about that from Mohammed. We can actually have a frequency domain analysis or a time domain analysis. And of course, seismic analysis can also make use of dynamic analysis procedures. I'm just going to run down on cable structure analysis just to lead into that. So cable structures are of course non-linear structures. So if we get going with cable structure analysis, we can start off with a weightless cable just subjected to a series of point loads, and this we can do with our normal basic statics, vertical equilibrium, horizontal equilibrium, and our moment equilibrium. And here we have our tension force, horizontal tension force in our cable, which of course determines the shape of the cable. And you can, for example, solve a structure like this as well, but now we're assuming weightless cables just to get going. The next stop is the so-called parabolic cable representation, where you assume that the loading on the cable is distributed horizontally and not along the cable profile. And then you can work with this equivalent beam to calculate your nominal vertical reaction forces. and then you add the effect of these horizontal tensions, and you end up with your final shape of your cable, as well as your tension at A and tension at B. Of course, this cable now is not, it's a step cable. The point B is higher than point A, so we can see that the tension force at B will be larger than the tension force in A. It's not a horizontal cable. So here's the basic equations for a parabolic cable, either taking the origin at the left-hand point or the origin at the middle. And there's our horizontal tension. The horizontal tension is linked to the sag, where D is the maximum sag of the cable, and L, of course, is the span, and W is the load per unit length horizontally. And we can calculate our maximum tension. We can calculate our cable length after the sag has taken place using that approximate formula. Inclined geometry and forces in cables. Of course, the moment you go inclined, the math gets a bit more difficult, but that can also be done. And then, of course, we need, in cases where one has quite a large sag in your cable, they say it's exceeding a factor of 8 above your a factor of 8, sorry, 1/8, a factor of 1/8 of your span, then you need to start thinking about using the so-called hyperbolic cable representation. Then your equation of your cable profile looks like this. You have this cosine, hyperbolic cosine in your solution of your differential equation. And now everything mathematically gets a little bit more difficult, but you probably need to do that when you run into a cable which has quite a serious sag, and then you talk about the catenary formulation, which is based on this hyperbolic cosine math expression. Then, of course, if you end up with a combination of point loads and distributed loads, then the next stop is you need to start working on in the finite element environment or the cable element environment. This is just a very basic cable element with 2 nodes, 2 displacement degrees of freedom per node. It's just 2-dimensional forces at the end of the cable. And of course, to model a structure using this very basic cable structure, using this very basic cable element, you actually need to divide your structure in quite a large number of elements. One can also, of course, get 3-noded and 4 and 5-noded. I think the one program even has a 7-noded cable element to represent cables which are, where the curvature is quite severe. This was just an example which I took from Strand 7's manual, showing a ski lift cable structure which was analyzed using finite element model. This is just the solution for the actual forces in this specific cable. And there's the stresses in the supporting towers for this cable structure. So we into the world of non-linear structural analysis when we work with cables, and of course then we need large displacement analysis. Typically we have small strains but large displacements. So we are going to work using our Newton-Raphson approach. It's an iterative process to solve our problem, and it's unlike linear analysis. Non-linear analysis requires multiple iterations with load increments to solve our problem. Use a tangent stiffness matrix. So that means the stiffness matrix is recalculated at each step of our iteration. This is an option. Some types of algorithms don't do that, but you can typically assume that when you have large geometric deformation, then you need to do that. And then you have to calculate the residual force error, and then you go ahead and check your convergence criteria if you're happy for the point you're in your solution, and then you step to your next load step. So if graphically, this is a very cryptic representation here, but the Newton-Raphson approach is we apply a load increment, calculate the displacement increment, and then we step after each load step. After we're happy that each load step is converged, these little lines over here represent these steps we take inside each load step. Then we carry on to our next, load step. Software. I want to say a little bit about software. So there are quite a number of dedicated software products around for tower and mast analysis. Bentley has got a product called Open Tower Designer. There's a thing called TNX Tower, ASM Tower. Safi Telecom also has a product, and then TS Tower by TowerSoft. And then Global has an RF Tower add-on, which one can also use. I just had a look at their website. I haven't used any of these specific products, but there's an example which ASM Tower shows on their website. The first one is this is a guide pole, And this is a strutted pole, 12 meter high. And here they've got example of how they actually do their footing design and analysis. And there's another one with base connection for a monopole, which they model in this software. As far as general purpose software is concerned, finite element software, I've had a bit of experience in Diana, which is a product originating from Delft in the Netherlands. And then, of course, Strand 7 is also very capable as far as nonlinear analysis is concerned. It's a product which originates from Sydney in Australia. But both of these products are quite capable to do any large displacement analysis required for cable supported structures and towers. On this, I'm just showing you Diana's user interface, which was upgraded in the past years to be actually very useful. And this is the Strand 7 user interface, which you can also use to model your structures and do all your calculations and non-linear calculations. So on the fabrication and construction side, I just wanted to mention that there are quite a number of ways to get a tower up. You can manufacture components on the ground and add them up, and then use a crane to place them, or you can use something like in this case, a self-supporting crane to get your tower up. So this is also, I think, with the advent of mobile, very powerful mobile cranes, this probably doesn't happen that often. But of course, you might have sites where your mobile crane can't reach the site, and you have to make a plan to erect your tower. It's also an option of a so-called tilt-up method, where you can build sections of your tower on the ground and then have a system of cables to lift this thing up. And as I've said, mobile lattice boom cranes, self-erecting towers. You can even, of course, use helicopters to place certain components on your tower. Especially might be when you get to your equipment, your electronic equipment, you might need an helicopter to actually get it placed on your tower. As it says here, there's quite a lot of considerations one must think about. Is this tower and the partially constructed tower going to be stable? What's happening on site? And where is the site? And then, of course, personnel safety is a very important aspect of the whole construction process. So this is just not a very good picture, but using an idea of a cable stayed tower being erected, where you use the guy cable, or might be an extra guy cable to actually hoist your component of your tower into position. I just to finalize my presentation, I was just going to give you two examples of failures. The first one was a 132 kilovolt steel pole line, electrical transmission line, which failed in Namibia in 2010, and this was definitely due to vortex shedding. You can see what happened, and quite a number of these supports poles collapsed. There's a few photographs also of the damage which was done as the poles one after the other in a sort of a progressive failure happened in this case. This is the finite element model, which was constructed to demonstrate the effect of the vibration on the structure. Of course, the structure vibrated due to the vortex shedding, and eventually metal fatigue set in, and these poles just snapped. On the right-hand side, you can see at the corner here, you can see the transverse displacement, which of course eventually caused the metal fatigue, which went into the collapse of these structures. This is another structure which collapsed in July 1998 at Gordons Bay Furland Service Station. The problem is here that there were 4 angle irons which supported this tower here, and they were not linked as a unit. That means that your total torsional stiffness of this structure at this point here was just a sum of four angle irons, instead of having a link there which connected them together. And of course, then your torsional stiffness would have been much larger. So once again, vortex shedding, which was working on this, the wind pressure working on this structure. And after a while, of course, then the metal fatigue set in and the structure collapsed. Last one I just want to talk about. This is the Quiche Solar Tower near Uppington. This is an interesting structure. It's about 200 meters high, concrete tower. And it has this, during construction, it had this tower crane connected to the structure at certain points, which was used to erect the structure. And then there's just another view of the structure. The whole idea is that the solar energy is reflected from these mirrors at the bottom here get concentrated on this collectors over here, and then there's a whole thermodynamic process where this heat is transferred to the bottom of the structure, where you have a normal thermodynamic electricity generation system, and the system also has a reservoir with molten salt, which gets heated during the day, and this salt is then after the sun is set, the molten salt is also used. The heat stored in the molten salt is used to generate more electricity, and I think this tower can generate electricity till about 10 o'clock in the evening before it then stops, and then it restarts again next morning. So what happened here is that there was a major thunderstorm, and this tower crane became dislodged from this concrete tower. You can see here what the massive scale of the disaster this was. There were actually 2 people in the construction office or the site office, and they were killed because this tower crane collapsed right onto this tower, right onto the site office. There's another photograph of the aftermath of this thunderstorm. Some a little bit more close up. As you can see over there, this was a massive disaster. I probably put this construction work back for at least, I think, 12 months, if I'm not mistaken, because this happened in 2014, and the structure was only completed in 2016. So this is a 3D model of the structure. We just did some work on the structural analysis of the concrete tower. So here you see buckling analysis on that tower, and once again we have this torsional behavior of these on these supports for this tower, which the structural engineers had to look into and make sure that there's reinforcing and designs could accommodate this behavior. There's just some vibration modes which you see for the dynamic analysis of this concrete tower. You've got mode 1, 2, and mode 10. Mode 10 is an interesting one where your tower shape is actually now changing. Maintenance, I don't need to say much about that. Maintenance activities, inspection, tightening of bolts, foundation maintenance, corrosion control, guy wire maintenance, safety equipment, availability of safety equipment, lighting systems on these towers to actually warn aircraft about their proximity, and then maintenance manuals need to be available so that people can know what they're doing in this environment. And as far as maintenance is concerned, at the design stage, one must probably think your work through and make sure that you're going for minimum maintenance, because lots of these structures are in environments which are difficult to reach. So we're thinking about galvanizing, painting, secure access systems, and then avoiding water traps which might cause corrosion and also other problems. And then also ladders, platforms, and antenna supports are things which also need attention, and make sure that they are properly fixed to the structure, that they don't cause problems. And the other thing is the mixture of materials. If one has some part of your structure in stainless steel, or might be some part of a specific steel making up your cables, you must make sure that you don't end up with so-called bimetallic corrosion, where two metals are interacting and causing the corrosion. And of course, then your protective, we heard about our greased cables, so the protective treatment on your guys and their fittings is also very important in the long term to make sure your structure survives. References, I've just put 2 down here. There's a book by Smith on communication structures published by Thomas Telford in 2007, which has got a complete sort of a encyclopedia of topics on this work. And then there's a book by Max Irwin, a very well-known theory book on cable structures, which is quite seriously, it's quite difficult to actually read. But this book, I don't know if there's any sort of serious cable structure mathematical analysis book published after 1981. Okay, Mr. Chairman, that brings my presentation to an end.
Thank you very much, Doctor. I think then we'll just go directly, Dr. Mohammed, if you can then just go on. Sorry, we were running a bit over time, but I think it's quite an interesting topic we're talking about. So, Dr. Mohammed, the floor is open to you.
Yes, thank you so much, Chair. Let me share my screen with you. Okay. Mr. Chair, can you see my screen, please? Just confirm.
Yes, we can see it.
All right. All right. Thank you so much. Good afternoon, colleagues, students. I am Mohammad Purbehi. I'm a senior lecturer at Cape Peninsula University of Technology, and I'm so happy to be here today to present my talk about digital twin for structural health monitoring and predictive maintenance. All right. So in this presentation, I'll look at. I will start with why digitization is becoming unavoidable, particularly in South Africa's critical infrastructure. Then I will discuss current roadblocks to digital transformation. And from there, I will explain how we developed a digital twin solution, of course, an affordable one. I see that many students are in this webinar. There would be lots of learning curve today. For this digital twin solution for structural health monitoring and predictive maintenance, demonstrates its capability through a lab-validated prototype. If I have time, I will try to have a live demo. I brought all the sample to my office. It was difficult, but I will try to have a live demo of what has been developed so far to share with you some insight, and then I will look at the key findings of this presentation and the future contributions. So, as it was mentioned in the previous presentation by Syntec and by Dr. Shasa and my colleagues, as you know, South Africa is growing dependence on energy, water, and telecommunication infrastructure, demands high reliability, and demands, so no excuses. It's very important. As we migrate toward 5G networks and IoT-enabled systems, telecom towers are being upgraded, reloaded, and reused at unprecedented rates. Yet, structurally, we still, unfortunately, rely heavily on periodic inspections, which are costly, labor-intensive, and reactive. The absence of real-time visibility means damage is often detected late, sometimes after service disruption or failure. This, of course, exposes a clear research and industry gap, as it was mentioned by Nkile. An affordable, scalable, fourth industrial revolution solution that enables continuous monitoring and predictive maintenance, of course, required. So that's the gap that we set out to close with a practical digital twin approach. Even though tower owners are willing to embrace digitization, adaptation has been slow. Why? We should look at the answer by this factor that the data is often fragmented and missing or inaccessible. During mergers and acquisitions, critical digital information is lost. New owners inherit paper records, PDFs, 2D CAD drawings with no single source of truth. The consequences are well known. Inaccurate equipment inventories, poor collaboration between stakeholders, designers, office designers, constructor, and manual error-prone processes and escalating operational expenditure. Without reliable and structured data, making informed structural and maintenance decision becomes both risky and expensive. So the question is that why we need a digital twin, even though that we there are lots of discussion, as you have seen it recently in social medias, in universities, research institutions, but so far you might have seen that there is no tangible solution to it. Everyone is talking about digital twin solutions or virtual twins, but we are looking at the real application of digital twin. But before that, I would like to take you through some history of the digital twin, how it becomes like in this stage right now in the world. A digital twin is a living computational replica of a physical asset. It's continuously evolved using sensor data, modeling tools, and analytics. In our case, this includes accelerometer data from IoT sensors, structural models built using finite element method, and cloud-based analytics. Unlike a static model, a digital twin reflects the current condition, not just the original design. It captures the past, present, and predicted behavior of the structure. In essence, it allows us to see, understand, and anticipate how an asset behaves, not just making a guess. The concept isn't new. In the 1960s, NASA, as it was explained by Dr. Streisheim, used in mirror physical systems during the Apollo missions, including Apollo 13, to troubleshoot failures in real time. In 2002, Dr. Michael Greaves, this person is actually the inventor of this technology. He coined the term digital twin, formally introduced the digital twin concept, describing a three-dimensional system, including the physical assets, a virtual model, and the data flow between them. By 2018 and 19, research done by various research, you are welcome to look at various research that has been done in this field, but most importantly, Tao and he expanded this into 5-dimensional digital twin, adding services, analytics, and prediction. Importantly, while global interest is growing, practical infrastructure-focused implementation remain limited, especially in South Africa. That's where this research work positioned itself. So why should engineer care about this digital twin? Imagine a structure where design, monitoring, and maintenance are connected. Data updates the model automatically, and damage is detected before it is visible. So digital twin supports smarter planning and design, reduce site visits during maintenance, and early detection of structural degradation. At scale, multiple digital twins from connected infrastructure ecosystems, a truly digital or virtually built environment can be built. So in summary, to just summarize all of these backgrounds and studies that have been so far, one can say that the digital twin is an innovative technology that can help solve infrastructure challenges by capturing past, present, and predicted future through the use of real-time and historical data, motivated by outcomes and tailored to use cases. A digital twin accelerates holistic understanding, effective action, and decision-making processes. From an operational perspective, digital twins may contribute towards reduction of unexpected failures, improvement of decision-making, and extension of asset life. Economically, they would shift maintenance from reactive to predictive, which directly reduces operational expenditure, especially for geographically distributed towers. Now, let's move towards what we have done in the past few years. While I joined Cape Peninsula University of Technology, I have a root at Stellenbosch University with a massive knowledge in finite element modeling, seismic analysis, working with Dr. Strassheim in computational lab. So building on those knowledge and combining the knowledge of seismic loading, finite element models, I came across this idea, why not building a solution that it's cost effective and can solve our problem here. Now I would like to introduce three potential technologies that later we'll see we can merge them together to achieve a tangible solution. First, the physical assets. As you see, the physical assets can be any infrastructure. It can be a tower in our case, and perhaps partially instrumented with sensors. I'm not sure if this is the case in South Africa. Second, finite element models that let us understand how these assets behave under stress and forces. And third, an IoT cloud that turns raw data into real-time insight. They are individually useful. Together, they are transformative. So look at the first product here is a physical asset. As you see, it's a tower. In telecom towers, these structures behave primarily as a cantilever, responding to wind and operational loads. By measuring acceleration, displacement, and rotation, we gain a continuous picture of structural health. But as you know, data alone is not an intelligence, right? We need to get this data into some insights. We need a structural brain. Moving here, yeah. The second component is a high fidelity finite element model developed by using any finite element software, as it was presented by my colleague, Dr. Strassheim. This model is tuned using experimentally measured natural frequencies. And also we need to consider very important aspect that I think Nkile mentioned something very important, why the results of the models are not similar. Why this is happening? Actually, in my experience, shows that many designers, they don't consider the right damping mechanisms in their systems, and even the model is not well tuned with the actual structure. This is the main problem. If we can find a solution how to tune our structures with the real one, and also define the realistic damping and for the energy mechanisms, energy dissipation system, then we hope that we get the same answer as we are going to try today. The results is a model that doesn't estimate, then it mirrors reality. This is something that we are looking for. Now let's give it live senses. The third component is the IoT. It's a nervous system. Sensor data flow from any sensors. In this case, in our solution, we use MPU 6050 sensor, accelerometer, and gyro with Arduino, ESP32 Wi-Fi, and we link it to a cloud system as an IoT. It's for free for educational for academics. If they use a MATLAB, for example, ThinkSpeaks one of the solutions that you can use it for free. Then what we do, this gives us a real-time dashboard to control the data and remote access. You can see your data from anywhere at any time. You don't need to be on site. You can send the data through your Wi-Fi system to the cloud, and then you can actually observe your data and any failure or anomalies in your structure. So we have continuous monitoring from lab to the field. So moving forward, I think now you see what's happening here. So far, in field of structural engineering, there are some professionals working on, let's say, in design office, and what they do, they just do the design. And some professionals, and especially with working within the field, they work through their experience to erect the towers or build them. And some of the professionals and engineers working through by installing some sensors on these infrastructures. But what you are trying to do here is a revolutionary solution that we can merge all of these three products together. And then I would like to introduce a digital twin system that integrates the physical tower, a structural simulation engine, and a cloud analytics platform. This model has been developed in my research lab at CPUT. And if I have time today, I will have a look on live demo and I will present some elements of this model. So this is where simulation and reality meet continuously. So now let's look at the inside of the system and what sort of elements we use. So this is a digital twin model that we developed. We combine physical model with a digital twin, and it's enabled with IoT predictive maintenance systems. All right, in the lab, we used a simple aluminum cantilever beam as a tower proxy. Just this is, you can, of course, you can, the next phase of our, the model that we developed is just using in a real case. Sensors feed data through Arduino into the ThingsSpeak cloud, which links directly back to the finite element software. In our case, we use Abacus finite element software to build our digital twin. This setup allowed repeatable testing and clean validation. As you see, these are the components that we use in our model. Moving forward, we operate a hybrid model, physical measurements, virtual finite element simulation, and calibration aligns with the twin's frequency and damping with reality, producing decision-ready behavior. The feature of our digital twin it's a new version of the digital twin that was developed just last year. We started with the initial ideas, but last year we brought it to the next version. So this is the reason why I say this is digital twin 2. It's a real-time structural monitoring by data acquisition, visualization, analytics, and planning, approval and engineering, and data. So yeah, you can make a link and a process in this regard. So this is the experimental setup that we have. Of course, this is the initial version. It's developed by my students at the research lab. Data is filtered using Kalman filter to capture some environmental noise and processed in Python and transmitted wirelessly in real time through the ThingsSpeak. So as you see, the next step after we collect the data from the cantilever beam, this is the most important part as we need to tune our structure. This is the part that I mentioned. Many engineers, they miss this part because what's happening, we create a model using a software, but we don't know that if that model actually resembles the actual structure. So we need to do some certain analysis here. We collect the data from the sensors and then using a special approach with mass and stiffness tuning in the structure to make sure that by doing a FFT analysis, you can do it with any software, we get the natural frequency of the structure through the signals processing, and then we try to match the signal with the one that we extract from the software. As Dr. Strauss, I'm showing a number of them. Those signals, those frequencies must be somehow resembles the one that might be on real structure. So by this technology, if we install those sensors on the real structures, by having these signals, one can mass tune the model within the finite elements or any other software, so that we make sure that the frequencies are in alignment. But the next part that is very important is the damping ratio. So we use a Rayleigh damping approach. I have developed a sort of a spreadsheet for this purpose. For those that have passed the dynamics of structures in their postgraduate course, you know that there is a theoretical background using the dynamics of the structures. One can find if you get a signal from the sensors, then by manipulating some data and using the dynamics of the structures theories, one can get alpha and beta for mass and stiffness coefficients. And then these damping coefficients can be adjusted in the finite element model. And then you make sure that you have a right damping neurostructure. So if I share this message today, I think I'm done more than enough, because this is most of the things that the model's getting messy. Please make sure that you have right damping in your models. So then now we have a digital twin here. The model that, for example, I use Abacus to make a realistic model of the physical asset. It's a cantilever beam here. I will show it later. Now we ensure that what we have as a displacement on these structures exactly showing the displacements that the signals that are installed, I mean, be captured by the sensor that are installed on the structures. So it is very important. Now we can do lots of practices. Now it's a we have a model that both frequencies and dampings are somehow close to the real one. Now we have this structure. We can do lots of scenarios. We can apply loads, seismic loads, and then we can get insight out of these real structures. So I'm going to stop here before I move forward for the final results. I'm going to show you what we have done so far. Of course, there would be more, perhaps a live session during the short course that's coming next month. But just for a demo, I would like to share with you some insight, what we have done so far. So I'm going to share my screen with you. This is a simple platform that we use here. And as you see, this is the ESP Wi-Fi that's get the MPU sensor installed on top of this cantilever beam. As you see, I fix it with the bolt at the bottom, so it's a cantilever beam, and this is about like 500 centimeters. It's exactly the same model, is aluminum, and the sensor MPU60 installed on the top. Now this system is connected to my computer, and through a code that we developed here using Arduino, I'm going to run it here so that you will see what's happening. And if I'm lucky, I did it before the start of the session. I hope that it's not going to disappoint me right now, but yeah, let's see how it goes. I'm running the code. It's getting compiled. Please give me some time. Yes, moving. All right, compiled successfully. Now I'm running the code. I'm waiting for a few seconds to get the signals from the sensor. All right, it's running successfully. Now we have run this model. The next step is a Python code that translates the signals from this software, Arduino software, to the visual visualization that we needed. I'm going to run this Python code. I hope that it's running again. Yes, the signal is coming. This is the signal. Now, as you see, I'm going to apply some sort of vibration. Let's say this vibration can be due to wind or any seismic loads. And as you see, it's live. So this information now can be used for like a starting point of your modeling. So this is very interesting. We are at this stage, and there are PhD students who is wishing to install this system on a real structure very soon. So it's coming in coming years, but through the collaboration with Centec, definitely more development will be done. So this is a real insight. So as you see, now the next step, unfortunately, I can't show you right now, but this information also can be sent to the clouds. Any cloud system, in our case, we use the ThingsSpeaks. It's a platform through MathWorks. It's for free for academic license. If you have it, you can use it for sending the data, but we have done it successfully so that you can share those information through the channel, that everyone at any time, anywhere, you can get those insights. So coming back to my presentation, as you notice, the key result is that we achieved high correlation between models, and minimal data latency, and a low-cost, scalable structures monitoring. With continuous data, we can detect faults early, schedule maintenance optimally, and integrate AI and machine learning for anomaly detection. This is the important phase that I would suggest students, especially postgraduate students. There is a great opportunity now. You have access to abundance of many synthetic data that you can feed to the machine learning and develop insights out of this using AI solutions. Some limitation of the model, as it was mentioned, is a lab scale validation, and it's Wi-Fi dependency, and it's tower only dynamics. So we are hoping with more collaboration with industry, especially with tower industry, such as Centec, we can get more access to more infrastructures and install this solution and get more insights. The next step is full-scale tower deployment, environmental load integration, AI-driven analytics, BIM and SCADA integration, and importantly, the same architecture applies beyond telecom. Thank you for your time. I look forward to your questions and discussion. Thank you so much.
Thank you, Dr. Mohammed and Dr. Breda. I appreciate you guys' time and effort you put into this, and I think for questions, I think we ran over time by quite a bit at this moment. I think what we will do is we'll take the questions offline. We'll reply on the chat and on the Q&A. So just keep it up there. But I would say a lot of you guys, if you're interested and you feel like you want to get into this type of engineering, please attend our course. Then I think most of also your questions will be answered there in more detail. And I'd just like to say thank you again for the presenters. I think there's a hand from Bile. Debbie, I think if you can unmute him quickly.
I'm going to do that now.
Yeah, I got. Yes, Bile.
Just a quick question. Good afternoon. For the course, do you perhaps have the link for us to register?
We will send out the advert probably in the next month. We will send it out for everyone, and then you can just keep your eye on our LinkedIn and on SAIC's email circulate will be on there. But I think what we'll try and do is everyone who registered for the course, I think we have everyone's email. We'll try and just also see if we can send it directly to you guys as well.
Okay, thank you.
But it's definitely going to be up the 15th and 16th of July. It's going to be somewhere in Johannesburg. We're just finalizing the venue, but somewhere like Midrand in between Johannesburg and Pretoria that we're aiming for. So you guys can sort of look at your calendars and block it out so far. Okay, I think then thank you everyone. Everyone for attending, and you guys have a nice evening. And then yeah, see you guys at the course then. Thank you.